Hello, everyone. My name is Xiaojie Luan, a postdoc student from ETH Zurich. My presentation today is about passenger-oriented traffic control for rail networks, considering crowding effects on passenger choices and on train operations. This work is done together with Professor Francesco Corman. I will introduce my study in these 5 steps. So the introduction of the study, the statement of the problem that we focus on, followed by the mathematical formulation, case study, and the main conclusions and the future work at the end. So first, the introduction. Why we study the passenger-oriented traffic control problem? This is because we want to improve travel experience of passengers. This is the aim of many train operators, like SBB, the Swiss Federal Railway operator. So improving the transport service quality for passengers in terms of punctuality, reliability, comfort, and so on. Increasing passenger satisfaction and attracting more people to use the services so as to increase their profits. In fact, we are still far away from this goal, as the traffic is practically controlled from a viewpoint of operations, namely minimizing the total delay of the planned schedule. In recent years, the study of traffic control problem tends to be passenger-oriented, switching the target of control decisions from the benefit of operators to the benefit of passengers. This bridges the supply aspect and the demand aspect, enable us to generate the train schedules in a passenger-friendly way. However, the inclusion of passengers into the process of train scheduling increases the modeling difficulty and the computational complexity. For reducing the problem complexity, some passenger-oriented studies focused only on the macroscopic infrastructure details and mostly neglected the vehicle capacity for carrying passengers. In those studies, they mostly assume there is sufficient space in trains, so the passengers of a group make exactly the same choice decision. No split. This assumption prohibits the use of such approaches in case of large passenger flows, as the passengers cannot be handled properly. As a matter of the fact, there are limited physical space in trains, and the passengers should make road choices based on resource availability. Moreover, more passengers in trains can lead to crowding issues, which can affect the choices of passengers as well as the train operations. Therefore, we studied the passenger-oriented traffic control problem by means of integrated optimization, particularly considering the crowding effects on passenger road choices and on train traffic. The decisions to be optimized include the train orders and the departure and arrival times, as well as the passenger choices on their itineraries. The goal is to find the system optimum by allowing flexibility in train traffic decisions. In the model, we assume that passenger choice is rational, so they choose their routes that minimize their disutility. And we assume passengers have good information on the train services, so they can react timely to any changes. In the objective function, we minimize the weighted sum of the total passenger disutility and the total train delay. The passenger disutility includes the sum of the passenger delay, the actual passenger travel time, the amount of stranded passengers with a large penalty multiplier, as well as the additional travel time that the passengers perceive caused by train crowding. Constraints are proposed for train operations at the microscopic level and passenger transition at the macroscopic level. incorporating the microscopic traffic regulations and the macroscopic passenger road choices into a single optimization model. The conclusion of the microscopic details guarantees the feasibility of the generated train schedules, while the inclusion of the macroscopic level reduces the complexity of rerouting passengers. Because passenger choices are at the station levels, they are not allowed to board or alight from any train at any segment, only at the stations. We use piecewise constant functions to describe the crowding effects on passenger choices and on train traffic. So basically, the train crowding is valued by using time multiplier. So passengers will perceive a longer travel time on a more crowded train. Similarly, we prolong the train dwell time at the station if the number of alighting and boarding passengers exceed the maximum flow that can be handled within the planned dwell time. In the model, there are some nonlinear constraints because we allow passenger groups to split, and also because the use of piecewise constant functions. We propose exact methods and use three transportation properties to linearize them. But due to the limited time of the presentation, I cannot introduce the details here. In the case study, we consider a railway network in the Zurich of Switzerland, including 7 stations. We consider 18 trains with different categories and 10 OD pairs with relatively large passenger flows. We associate each OD pair with 2 passenger groups. So in total, we have 20 passenger groups. We have 20 passenger scenarios. For each scenario, each passenger group is given a randomly generated departure time, at which the passengers intended to depart from their origin. The passengers in different groups, but with the same OD, have a minimum of 15 minutes of departure time interval. Also, we consider the passenger amount to be different in different scenarios. However, the passenger distribution per OD is constant. In the experiments, we consider 5 computational configurations. In configuration 1, we neglect the crowding effects. In configuration 2, we include only the crowding effect on passenger choices to effect the choices of passengers. In configuration 3, 4, and 5, we include the crowding effects on both passenger choices and on train traffic. The differences are whether we tolerate train delays. So trains can stop longer at the stations for passengers boarding and alighting, and whether we allow passengers to be stranded. According to the experimental results for configuration 1 and configuration 3, for configuration 1, 2, and 3, we can obtain the optimal solution very fast, within a few seconds. For configuration 4 and 5, we do not obtain the optimal solution within the 1 hour of computation time. So we report the best feasible solution find. Here we compare the results of the 5 computational configurations, representing the average over the 20 passenger scenarios. So when neglecting the crowding effects on both train traffic and passengers, see the results in the first row, we can obtain the solutions with the smallest passenger disutility. In fact, neglecting the crowding effect on passengers makes every passenger independent, so that passengers can always choose their shortest path without being affected by the others. In such a case, there is a concurrence of the system optimum and the yield equilibrium. If we include the evaluated impact of the train crowding on passengers, see the results in the second row, the passenger disutility becomes larger. For the configuration 2, the train crowding is considered as one factor that affects the passenger road choice. As such, some passengers choose alternative routes that are less crowded but have longer travel times and larger delays. So the sum of the passenger delay and the passenger travel time increases when comparing with that of configuration 1. The rerouting of those passengers leads to less crowded trains so that the passengers can overall suffer less from the train crowding. This leads to a significant reduction of the additional passenger travel time by about 40% from that of configuration 1 here. Overall, the total passenger disutility is also reduced by about 3%. In the solution of configuration 3, there are some stranded passengers. As we consider a large penalty multiplier for the stranded passengers, the passenger disutility of configuration 3 is much larger than the others. When allowing changes to the planned timetable, all passengers are transported, no longer stranded. In the solution of configuration 4 and configuration 5. In theory, the conclusion of crowding effect on train traffic may lead to worse situation, as the prolongation of train dwell time may cause train delays and even delay propagations, which further affects the journey of passengers. However, as shown, the passenger disutility of configuration 4 and configuration 5 is improved in comparison with that of configuration 1, 2, and 3, at the cost of some train delays. This improvement is mainly achieved by rerouting some passengers onto alternatives and by adapting the train schedules. So allowing changes to train schedules enable us to explore a larger solution space and bring more flexibility to serve the passengers better. So the conclusions. According to the study, we can conclude that the overall system performance can be improved by rerouting some passengers onto alternative routes that are less crowded but with longer travel times and larger delays. We also observed that if the train delay time is highly sensitive to the alighting and boarding passengers, the transport network will become less reliable, which should be avoided in real operations. Moreover, flexibility in the train decisions helps in improving better services to passengers. So providing better services to passengers. For the future research, we can develop solution approaches for improving the computational efficiency of the proposed model, for instance, using decomposition and a distributed approach. Also, we can consider a passenger behavior model in order to better reflect the passenger choices and capture various possible effects of the changes to the train timetables. In addition, we can investigate the social rerouting of passengers, so the strategies of steering some passengers to make reasonable detours for the benefit of the others and the improved overall system performance. So that's all my presentation. Thanks for your attention.